Stoichiometry. I hope you can pronounce that right. When we speak about stoichiometry in chemistry, that means it involves all the calculations related to getting the quantities of substances that are involved in a chemical change. So stoichiometry is the foundation calculations that we all need to be familiarized of, so that when we go to much more difficult calculations, we are pretty sure that we've mastered stoichiometry and we will be able to be helped in order to do the right calculations. So let me start by giving you the correct concept of the coefficients that we place when we balance the chemical equation. Now we know that we balance a chemical equation because of the concept of the law of conservation of matter or mass. It means that you cannot destroy nor create atoms in the process of a chemical change. So that means the mass before and after the reaction must be the same. So therefore, the number of atoms of that particular element before the reactant side, must be equal to the number of atoms of that same element on the right side. So all elements have to be accounted for, and it should be of the same number. So the basic thing that we know about the coefficient. So what does it mean? So when we have a coefficient of 1 for our N2 gas, that means it needs 1 molecule of your N2 gas for every 3 diatomic molecules of your H2 gas. Therefore, if you have this much of molecules in the reactant side, you will be able to produce 2 molecules of NH3 or ammonia gas. So that means this will be how it looks like. So you see that the 2 nitrogen are there, and you see that there are 6 hydrogen all in all there, because you have 2 of the NH3 molecule. So 1 molecule plus the 3 molecules of your N2 and H2 respectively will generate 2 molecules of NH3. However, we know for a fact that we cannot measure and isolate by molecule because we cannot count them, and they're very microscopic, they're very, very tiny. And so what do we do? You know from your mole conversion that it was Amedeo Avogadro who was able to relate our microscopic particles with a measurable quantity of mass. And we call that bridge to be the mole. So what if I will say that I would need 1 mole of my N2 plus 3 moles of my H2 to produce 2 moles of NH3. Now, if I have this, it will be clear that if I would need 1 mole of N2, all I need to do is get the mass of 1 mole of N2 gas. 1 mole of N2, so that means 2 times the mass of nitrogen will give you 28.02 grams per every mole of that. So for 1 mole of N2, I need 28.02 grams of that. If I would need 3 moles of H2 gas, how much should I measure? Now, for every 1 mole of H2, that is 2.02. But there are 3 moles of that, so I multiply it by 3. That means I need to measure 6.06 grams per mole of my H2 gas. That's the molar mass of my 3 moles. And for NH3, how much should be the mass of my product? So NH3, 1 molecule of NH3, that is 17.04 grams per mole. So for every 1 mole of NH3 gas, you have 17.04. Then I multiply it by 2, I would get 34.08 grams per mole. Now, what do you notice? You notice that if you will add 28.02 grams per mole and the 6.06 grams per mole, it will now be equal to your product's mass, which is 34.08 grams per mole. Law of conservation of mass is observed. So what is my point here? In order for us to do stoichiometry calculations, and when we relate our coefficients to the calculations, it's very safe and accurate to just say that these coefficients not just represent the number of molecules or the number of compounds because they're not measurable. So we can safely say that it represents the number of moles of that particular compound. So I need 1 mole of N2 for every 3 moles of H2 in order for me to generate 2 moles of NH3. So that coefficients represent the number of moles of that particular compound or molecule in your chemical equation. Why are these coefficients very important? Because these coefficients will be used later on for what we call the mole ratio. So every time you will meet the term mole ratio, always remember that it comes from the coefficient before you write the chemical formula. So let me just end by giving you the roadmap for stoichiometry. What do you mean by roadmap? This will give you an idea on what will we do every time we are drawn to calculate some stoichiometric problems. So we always begin with the one at the middle. So what does this mean? It means that we always begin with substance A. That means that's your substance given. And you will be asked to get substance B. Substance B means your unknown. So A is the given and B is the unknown. If you're given moles of A and you want to get moles of B, all you need to do is get the stoichiometric factor. Stoichiometric factor is just your mole ratio. I will give you more problems about this, but for now, please remember the roadmap. So to link mole A to mole B, all you need to do is multiply it by the mole ratio of the given substance with that of the substance you're being asked to solve. Next, what if instead of mole of A, the given, you're given the mass of A, in which your mass of A may come from density and volume. Take note, it's possible that instead of given the mass right away, you might be given density and volume. Please remember that to get the mass from density and volume, all you need to do is multiply your density with that of the volume so that you can get the mass of A. How do you now get from mass of A to moles of A? Very simple. Just use the molar mass of your A. Now we know for a fact how to use the molar mass or how to get the molar mass. Molar mass will come from the periodic table. It will come from the sum of the masses of every element that comprise your compound. So when you divide it with the molar mass of A, you will get the moles of A. Similarly, if you want to get mass of B from mass of A, so you still need to pass through molar mass and then go through the mole ratio, then multiply it then with the molar mass of B so that you can get the mass of B. And eventually, if you want to get the volume of B from the given density and the calculated mass, volume will just be mass over density. And that's how you get the volume of your B, the one you're looking for. So please follow this roadmap. When you are doing these calculations, it's mostly multi-step. That means multi-step conversion should be clear as to what you're canceling out. From mass to mole, you have to cancel out the gram to get the mole. Mole to mole, that means you need to come up with a mole of B, canceling the mole of A. And then eventually you want to get mass of B. That means your endpoint should be the gram of B. So therefore the gram here should be on top and then the mole should be below to cancel out the mole of B. Eventually leading you to the mass of B, which is in grams. Take note that you always have to have the final correct unit and canceling out the rest that are not used. Next, we can go further. Still, what if you're given the mass of A and we want to get the number of particles? All you need to do is still the same, multi-step conversion. After the molar mass, you want to get the number of particles, just use the Avogadro's number to get the number of particles. That's the same way if you want to go to moles of B and you want to get the number of particles of B, just use the Avogadro's number, canceling out what you don't need. So please remember this roadmap. I hope that you'll be able to use this when we do calculations later on. See ya.